Absorbance by who? Or by what? Surroundings, okay? It has gone to the surroundings. And how do we call that? What has gone, the energy that has gone to the surroundings? No? Entropy. Okay? So the energy that is not preserved on the balls and doesn't make the balls moving all the time around is because entropy exists, and therefore some of the energy every time it hits is transformed to friction that goes to the surroundings, and it's not being able to continue on the system. It goes out of the system, and that's what we call entropy. Right? So today we're going to see how we calculate the entropy of a system. And again, we are here looking at pure compounds. And we have more or less the same chart that we saw for enthalpy. So entropy will be a function of pressure and temperature. So it will be classified as a property of the fluid. And basically entropy will have an increase in entropy as the pressure increases, and an increase in entropy as the temperature increases. Right? So it will have an effect on entropy either through a change of pressure or through a change of temperature. What is this line that we saw last time? What does that line mean?
Latin.
This curve.
This is change of phase.
Change of phase. So here, this is the saturation curve or line, what we call. And basically, we're moving from, what phase do we have on this side of the chart? Liquid phase to a gas or vapor phase, right? And here, what do we have? A step change in the entropy. Why? What does it make it have a step change? What happens in the saturation line? We have the phase change, right? And that will require central enthalpy that we saw last time, and as well will produce an entropy. So this will be a step change where we have the phase change from liquid to vapor, right? So it's more or less the same type of chart that we saw last time. So how entropy changes with temperature and pressure. So in order to mathematically describe this process, we need to use this equation. So the change of entropy will be, again, we will refer to the heat capacity coefficient at constant pressure, Cp, over temperature and changes in temperature, and again the changes in volume over the dP. And here, this will be the same equation as for enthalpy, but here we will have the temperature in the denominator. Okay? There's something else missing on this equation. And what we are missing in this equation is basically the phase change. So the general equation of this, Cp over T dt minus dV over dt P dP. So this is the change produced by a change of temperature. That's the change in entropy by a change of pressure. And then we will also have an effect by the phase change. And this is given by the enthalpy of evaporation, which will be the phase change, over the temperature where we have the phase change. And this is what we will call the sensible heating. Okay, so the entropy will change according to the temperature, to the pressure, and as well as the energy that is input into the system where we have when we arrive to the saturation line, and then we have a phase change from liquid to vapor. So then here we have an example, right? So this example is solved the same way as we solved it for enthalpy on the last lecture. Do you remember how we solved for enthalpy? We normally, just to go back a little bit, the enthalpy curve, that was the process that we wanted to describe. So we were at a pressure and a temperature, and we wanted to arrive to another pressure and temperature. So instead of going through these lines that will imply a change of pressure and temperature at the same time, we'll basically divided the process through lines that will imply constant pressure and a change of temperature, constant pressure and a change of temperature, constant pressure and a change of temperature, and finally we had a change of pressure and constant temperature. Okay? So to solve the example that we have 5 kilograms of water at 450 kelvins and 600 kilopascals, and we want it to basically, yes, we want it to arrive to these conditions, and the entropy of water at 298 kelvins and 100.3 kilopascals atmospheric pressure is that one. So what will be the entropy of water at those conditions? So we're changing from atmospheric pressure as well as temperature, and we are going to a higher temperature and higher pressure. So what would you do to solve this problem? So at this point, you should be able to solve it. You have the equation, and then the conditions that we gave last time are here, right? So this is when we calculated the enthalpy change, and you basically will take the same equations and the same values given, as well as approximating the change of pressure using the virial coefficient, right? So here we have the solution. And as I say, the calculation is carried out in the same way as for the enthalpy. So we will have to heat the water up to its boiling point, 373 Kelvin, 100 degrees centigrade, at atmospheric pressure. Vaporize the water from at this temperature and pressure. This is the sensible heat of vaporization. Heat the vapor to a superheated vapor, which is further increasing the temperature to 450. And finally compress the vapor at 600 kilopascal. So it will be the same way that we went through the chart. However, in here, the thing that changes is basically the general equation, when we have here temperature dividing the factor. So let's have a look at the first way of doing it. So we have the heat of water at 373 Kelvin. And we were given this equation, which is the...
What is it given? So heat capacity
the heat capacity is given here as an equation which is a function of temperature. Okay? So this was given, if you look it here, it says use data given previously. Okay? And that was given on when we were looking at the enthalpy, and we were given the heat capacity using those equations. So basically we need to use the same equations, the same data, right? So we input the equation in here, and we integrate the equation from 298 to 373, so we stop at the boiling point. So that's the entropy generated from the initial temperature, atmospheric temperature, to the boiling point. We integrate the equation and we substitute the data. Obviously here will be from a natural logarithm of T2 minus T1, as well as this coefficient times T2 minus T1, but here we're expressing that by looking at T1 and T2 in here. And then once we substitute this data into the equation, then we get this change in entropy, right? Then we continue moving on the chart, and then we are going to look at the entropy to vaporize the water, so to have the phase change occurring. Entropy of vaporization, which is a function or calculated by the enthalpy of vaporization over the temperature. Again, the enthalpy of vaporization was given, and in real life, if you weren't given that, that can be found on tables, on charts as well. You apply the equation and you get the entropy needed to vaporize the water. Then we go to heating the water vapor to 450 Kelvin. So we are heating more the vapor. And here we had an equation as well. The Cp was defined as a function of temperature for this further heating. Then we use the same equation. We have constant pressure, so the equation will only be a change against temperature, and therefore we have the temperature. We substitute. This is basically a mathematical working, and then we get this change in entropy. We have looked at all the changes against temperature, and finally we need to compress the water at 600 kilopascal. So for here we will look at the change of pressure, how the entropy changes through a change of pressure. And here we will substitute the virial equation of state that we saw last time, that is applicable to enthalpy as well. Solve this virial equation of state and get the entropy for that part. And just to look at the workings, it's very important that you look how this has been worked, okay? That it's solving there for you, but you have to look to it by yourself. So basically we started with this equation, and then we can take out what actually is changing in here. So in this equation we have pressure over here, and that will be the only variable that we will take over dP that will change. So here we take out the R, and as well obviously here we will have a constant. So basically we will be R dP over P plus integral of dP. So here will be plus dP, right? So over here that will be the integration of the first part, which is that one. And this is the integration of the second part, which is that one, right? So at the end, we basically look just at the sum of the entropy changes, and we have that general entropy. You can see here as well the units. Here we have everything over joules per kilograms Kelvin. And basically, to get joules per Kelvin, we multiply by the mass flow. So the mass flow was given here, 5 kilograms. In this case, it's the mass. And then we multiply by 5 kilograms, and then we get everything on joule Kelvin, right? So Kelvins appears in here. The units are different because of the temperature that we are using on this equation. So if we look at it, we're basically using this equation, right? But we are fragmentalizing the equation and working each part of the equation separately by looking constant temperature, constant pressure. We're basically taking out some of them. And at the end, we're adding all of them up together. So that's basically what we're doing. Instead of using the equation, go solve all these equations, which will be quite a large equation, complicated to solve, which could provide certain errors, then we divide each part and we are working each part, and at the end we are adding them up to get the change of enthalpy. Here we look at it like that because we haven't solved the derivative, but once we integrate, then we get delta S, right? And that's basically all regarding enthalpy and entropy. Okay, so we are looking at how the enthalpy and the entropy of fluids, obviously on a single phase, is changing when we changes the temperature and the pressure in the system. And that's basically what happens in a oil and gas processing. Okay, we go through all this equipment, and while the fluid is going through this equipment, is having a change in pressure and a temperature, and we want to know what is happening to the fluid through those changes. And through the calculations that we have seen of enthalpy and entropy, we are actually able to see what is the phase change, if there was a phase change, and what is the energy that the system perhaps will require, or what energy I'm putting into the system, and how this is affecting the change of the fluid. So obviously, for the terms of heating, when we were heating the water, is reflecting the works of a heat exchanger, and when we are compressing the water, is reflecting the works of a compressor. So now we're going to look at mixture properties, right? So everything is quite simple when we are looking at a single phase, when we have only a liquid, when we have only a gas, which applies in certain cases, but in most cases, especially when we look into oil extraction, we have mixtures. We have multi-phase flows, and sometimes these charts that we initially saw, they don't apply to mixtures. Okay, so mixtures complicate the process, and we're going to have a lecture on mixtures later on, but here I'm going to show you some essential things of how the things change in a mixture. So in chemical industry, we're always dealing with mixtures that contain more than one chemical species. So salt and water, oil, all of that will be a mixture of several compounds. So things do complicate. So normally, in order to facilitate calculations, we can, in certain cases, knowing the limitation, refer to it as an ideal mixture. Okay, so an ideal mixture in the gas phase will be when we assume that the atoms or molecules are so far apart that there's no interaction forces. in the opposite, in liquids and solids, we assume that the atoms and molecules are so close that there are no differences on the interaction forces. Okay? So basically we're saying if you have a gas phase, there are no interaction forces because they are far away. If you have a liquid, they are so close together that there are no changes in real interaction forces, so they remain constant. So it's more or less the same assumption, but one saying they're far away and the other one saying they are together, right? And then we said, actually, when we were looking at the internal energy U, we say that the internal energy is provided by these interaction forces that the fluid has, okay, together. So here we are assuming basically that that doesn't affect the system. And that helps us because then we can calculate the enthalpy and the entropy of a mixture just looking at the enthalpy of each single compound, multiplying it by the percentage of that compound and adding them all together, which really it's a very easy way of looking at the enthalpy and the entropy of mixtures. And here is the equation that I'm referring to. So basically here we will have the enthalpy of a mixture will be the sum of the enthalpy of each one of those compounds times the fraction of that compound. Okay? That will be for liquid and solid, and for a gas the same thing applies. Right? So xi and yi will be the mole fraction of the component number I in the mixture. Okay, so normally we do it by mole fraction instead of by mass fraction in order to take into account the effect of the changes of molecular weight. HIT will be the enthalpy of the pure components at standard pressure and temperature of the mixture, as well as the enthalpy. So here in the liquid, then we will have the same thing for the entropy. The entropy of the mixture will be the sum, again, of the entropy times the, well, this is solving the equation, and the mole fraction of the entropy. And then here, on the entropy of the gas, we will take basically the partial pressure of the gas, because that will also affect the gas in the system. Okay, so that's the only change between one and the other. So we'll take into account the mole fraction, but also the partial pressure of the gas to define what is the actual fraction of it in the system. So by using that assumption, then it really facilitates the calculation of a mixture in terms of enthalpy and entropy. So now there is an example. So we have a mole fraction. Some of you may already know that, but for those who need a little bit of reminder, so the mole fraction will be the number of moles of component I over the total number of moles, so a percentage basically. And here we have an example. Find the mole fractions of water, methanol, and ethanol. Suppose that we have a mixture of those compounds in 10 kilograms of a mixture with the following composition. So the composition is given in percentage mass, right? So we need to change that at percentage mole. So can you do that quickly, please, and give me the... But to this will be a change of entropy that is negative to the ceramic. So there always will be a positive or a negative entropy. The way that process will occur spontaneously will be always towards the change of entropy. So that means that you don't need any energy to generate the entropy. So here we are compressing the water vapor to this. So that compression is spontaneous into the vapor or not. Can the vapor compress by itself? No. Can the vapor expand by itself? Yes, the vapor can expand by itself, it can expand, but it cannot compress by itself. So if you have an expansion, you will have a change in the viscosity. If you have a compression, you have a negative change of entropy, which means that you are actually applying energy to the system for that. That's why it's negative, okay? So here we're looking at what's happening actually to the vapor
During compression.
during compression. So every processes cannot occur if you have a negative change. They cannot occur without any energy. So here that means that this process cannot occur spontaneously and you will need energy. Now you will have it as the yes. So by that, when you apply it, then it will reflect that is not in the equation. So yes, this kind of for compression it will be negative, for expansion it will be positive. Because the vapor can expand by itself. Yeah? You want? You need a handout? Yep. Let me see if yeah, that's it. Yes. No, that's mine actually. This Oh, I didn't bring more. It's over. I'll bring them the next session. Okay. Or in the break, you go and take copies of it. Okay. Right. So, two things. That some of your colleagues have raised. So, yes, I don't know why in your handout is, oh yes, here this should be entropy, please. Okay, so it's written wrongly in there. Change that to entropy. S is always entropy, right? And the second part, one of your colleagues asks why this change in entropy is negative. Why do we take it as negative? Can somebody answer that? Why the change in entropy is negative there? Here, somebody? Say whatever you do.
The reaction is spontaneous, the process is spontaneous?
Right, it's something regarding that, but that's not right. When it's negative, the process is not spontaneous, it's the opposite, right? So we always said, when we were looking at the second law of thermodynamics, that a spontaneous process will always have a positive change of entropy, right? So if we were expanding the gas, will that be negative or positive?
Will need to be negative.
If you have the gas in a small chamber and then change the gas to a big chamber, do you need to input energy to the gas in order for it to expand? No, it will expand spontaneously, right? So expansion of a gas will have a positive change of entropy. That means that you don't need energy in order to generate that effect. If you compress a gas, can that occur spontaneously? Can gas say, oh, I'll compress by myself? No, you need to have energy into the system to compress it. And that's why it's a negative change of entropy. So a negative change of entropy is telling that you will need to input energy into the system in order for it to occur. Right? And that's basically what happens from the second law of thermodynamics. So go again and revise the laws of thermodynamics, because those will be very important for you to know throughout all this course. Okay? Right, so you look into the mole fractions. So can somebody tell me the answer of this? What were the mole fractions that you obtained for water? Sorry? 58.9. Let me just... Okay. 58.9 for methanol. 29.2. Yes. And for ethanol? 11.7. Right. Yes, that seems fine. Okay. So let's go to the next example. And then here we have a mixture again, and we define the enthalpy and entropy of a mixture that contains 59% of water, 29% of methanol, and 11.8 mole percent of ethanol at 331 Kelvin and 101 kilopascal. Okay, so here we have the enthalpies and entropies. And then we have the formal enthalpy and formal entropy and the heat capacity. So just draw the equation that you will use in order to solve this system, okay? So just look at how you will solve it, more or less the structure, and write down the equations that you will use. Right, so a little bit, I'm not going to go through the whole solution, but basically you will have you need to obtain the enthalpy of every one of the phases at 331 Kelvin. So for that you use Cp delta T, which is what we saw. You are given Cp and then the change in temperature that basically will provide, and then you obtain for each one of the phases what will be the enthalpy of each. And then you multiply by the mole fraction, and the sum of it will give the enthalpy of the mixture at the temperature that you are obtaining. Okay, so you just have to apply that equation in order to look at the enthalpy changes, and the entropy will have more or less the same workout, but now using the equation over T that we saw. So go through it by yourself, and then if you have any doubts you can tell me. Okay, then we will discuss mixtures as well. There is like 2 hours just for mixtures, so this is just a brief introduction of what we will do later on. Okay, so right, so let's go to the next part of the lecture. Just I will start it and then stop to give you like 10 minutes break. And the second part of the lecture is basically thermodynamics of flow processes. Okay. So again, a reference that I use a lot when I was explaining the first and second law of thermodynamics is Smith, which is quite a good book, so I will recommend it. Just go and read it by yourself. Although there are certain sections that explain things that perhaps are not that relevant for the first and second law, but just look at the ones that will be. And this is a little bit more simple to understand, less complete, but again, you can read over there. So we go back to the oil and gas processing from the well, and that's going to be basically the system that we will be looking at throughout all this module. And we will look at how the properties of the fluid changes while going through the system, as well as, let's say, if we wanted to have a change in the fluid, how much energy will you need in order to generate that change in the fluid. Okay, so that's basically explained through the enthalpy and entropy that we saw in the system. But now we are going to directly apply these concepts to a heat exchanger, how we calculate energy needed in a heat exchanger, how we calculate the energy, the work needed in a compressor, again, how valves affect the fluid, and how the fluid is affected while going through a pipeline. So all these systems will basically apply the concepts of enthalpy and entropy and the equations, and the only thing that is going to change is how we treat each system. So if you have very clear these 2 concepts that we initially saw, then it will be a matter of just seeing how it's applied to different types of equipments. There's no point of looking at each equipment individually and say, okay, this is the equation for this equipment, this is the equation for that one. Because at the end of the day, you should be able to more or less derive and understand these expressions for any equipment. And if you really understand the fundamentals, then it doesn't matter that we don't cover everything. You will be able perhaps later on to work out any type of equipment that you occur or you have while working in this field. So we will have a look at heat exchangers, pumps, compressors, and valves in this part, and we will have how we establish the principles of enthalpy and entropy on all these equipment, and all these, we will start having a look at it just looking at a single phase fluid, but or a single fluid that is not a mixture, but they will be valid as well for mixtures. And again, the basis of all of the calculations is a combination of energy and entropy balances. Okay, so basically how these energy are influenced by the changes in temperature and pressure, and how this will affect the fluid, or how much heat input or work input I will need or I will produce from the changes in the fluid. So let's go back to the heat exchanger and expander. And in this heat exchanger and expander, we can draw a boundary, okay? So we will start with heat exchanger and expander, so we draw a boundary, and in this boundary we will have a fluid going in at certain pressure, temperature, velocity, potential energy, and enthalpy, and it will go out at a different pressure, at a different temperature. Kinetic energy normally in this type of systems is not considered to change a lot. Potential energy, again, it remains more or less constant, but if we consider it that is changing, then that's it. And the enthalpy change. So the enthalpy will be different of the fluid depending on how much work is done, or heat is input and work is input into the system. Okay? So this will be worked out through the laws of thermodynamics, enthalpy and entropy, and energy balances. So there are two concepts that we are going to learn. How to do that, we need to know how to do energy balances and how to apply these concepts into those processing units. So again, if we refer to the general equation that we saw when we were looking at enthalpy and we started looking at energy balance of a system, then we basically have the first law of thermodynamics. Energy in will be equal to the energy out. Okay? In this case, well, we have the energy in plus the heat flow and work will be equal to the energy out of the system. Okay, so not apart from enthalpy, there can be changes in potential energy and of kinetic energy. So the U denotes velocity, the Z is basically the distance or the height between equipments, and H is enthalpy. All of this is normally given in joules per kilogram. So you normally will do all your calculations in joules per kilogram, and later on, if you want to know the amount of energy, then you multiply by the mass flow and you get joules per second, or by the mass and joules, right? So that will be the mass flow rate. So here we're multiplying by the mass flow rate, and if we have the mass flow rate here, then the units will be joules per second most likely, okay, rather than joules per kilogram. So if we have joules per second, what will be the units of Q and W?
Joules per second as well?
And that is, joules per second is watt. Okay? So normally this could be given as watts. And if you have watts, you know that is joules per second. And sometimes in industry, they give you most of the time watts. Okay, if you buy a compressor or you buy a heat exchanger, they will always mention watts, not joules per second. Right, so in this system, normally when we look at the energies of those systems, the kinetic energy, because here we are going through a pipeline in most cases, and then we go through the heat exchanger, the area of this heat exchanger will be always bigger than the pipeline, and therefore the changes of energy due to the kinetic energy are insignificant. So they are taken as zero normally for equipment processes of heat exchangers and compressors. Okay, we can account them and we can calculate that if we go through a detailed design of the system. However, for our purpose, which is at knowing energy balances and the most significant ones, we will take as if the kinetic energy remained constant while going through the heat exchanger or compressor. The same occurs with potential energy. There is no change in height really between the fluid that is going inside to the fluid going outside. So therefore, the potential energy will remain constant while going through that. So if we take the kinetic energy and the potential energy to remain constant, these factors are taken out from the equation because this is equals Z2 times the gravity equals to Z1 times the gravity. So they go out of the equation, and this kinetic energy will go out of the equation as well. Okay, so therefore we will end up with this equation. Enthalpy at the outlet will be equal to enthalpy in the inlet plus any heat or work that is provided to the system. So then we have delta H equals Q plus W. Okay. Right, so here we have examples of heat exchangers that are used in industry. So the first one is basically the shell heat exchanger, which is a cylindrical heat exchanger, and it will consist of a number of tubes going through the heat exchangers with normally a U shape over here. So the fluid will go in, will go through all the tubes that are inside the heat exchanger. So this is a tube and shell heat exchanger, and basically what will make this heat exchanger work is that we normally pass one fluid through the tubes and another fluid through the shell, and the fluids get in contact through basically the material or through the transfer of heat that is produced by the change of temperature of the fluids, and we will basically heat or normally they use for heating or cool down in the case of the other fluids, any type of system that we want. So these type of heat exchangers are highly applicable in the oil and gas industry, and this is because they can withstand changes at very high temperatures and pressures. So they are normally a robust system that can withstand high changes in temperature and pressure. So the heat transfer will be across the wall. Here we have how it will look from the outside. So we'll have an inlet and then an outlet, okay? As well as for the other one. Then we have another type of heat exchanger, which is the plate heat exchanger, and that's basically used for moderate changes in temperature and pressure. And here we will have a series of plates, and these plates will be basically intercalating, and one of the fluids will go through one plate whilst the other fluid goes to the next one to it. They normally have a cross flow, so while one fluid will go up, the other one will go down, and so on. So we will have a series of plates connected together depending on what is the contact area that we require in order to achieve the temperature that we want. And these will be used normally for temperatures lower than 100 degrees Celsius. So when we don't have a phase change on the fluid, and pressures of around 10 bar, more or less. So it's used a lot for water heating applications, right? While this one will be used for different type of fluids that you want to heat at higher temperatures and pressures. So to design this heat exchanger, we can take 3 or 4 lectures. and calculate the number of tubes that we want, the area at the end that we need for the heat exchanger, and design all this type of system. That is not the purpose of these lectures. The purpose of these lectures is to look at those systems and just calculate what will be the energy that will be needed to operate, or what will be the changes in entropy and enthalpy that will be produced from one fluid to the other. Okay? And that's basically doing just the energy balance of the system. So we look at the heat exchanger, the fluid that goes in and out, and in this case, well, if we are removing heat or adding heat, in this case it shows heat removal, then we will have a heat load, and normally this will be given in watts. Heat transfer, we will refer to it at happening at almost constant pressure. So there is very little change in pressure between the inlet and the outlet of the fluid. And therefore, no work is done in a heat exchanger. So basically, as it says, Q will be the main important factor in here. So the enthalpy balance for here is M change in enthalpy will be equal to the heat transfer in the system. Okay. So again, for single phase fluids or for single fluids, then we can represent that if we take a slice of the diagram that we saw initially, for example, for entropy that we saw in the previous one, then we'll take this diagram and then we can have the piece of the cake. This case will be the liquid, so it's this side of the chart. That case will be the vapor. And this is this part of the chart where we have a mixture of vapor liquid. And if we are located at a certain temperature with this line, then we can obtain the entropy of the liquid and the entropy of the vapor. The critical point is where the entropy of the liquid or vapor will be the same. So here we don't have to go from one side to the other. It's exactly the same. And that's normally achieved at supercritical conditions. So a graphical representation of what is happening in a heat exchanger can be observed through these charts. And you can see those charts shown in a lot of textbooks. However, these charts are not applicable as soon as you have multi-component fluids. So they're nice to see and read, but when you have multi-component fluids, they're not very useful. So we'll stop here for 10 minutes and we'll continue at 10 past 10. For those of you who still need a handout, you can go to the school office here of Chemical Engineering and take some copies if you want in this break.
For this, so I'll just walk it out and see if I can
Yes, work it out. You want the answer? Oh, I haven't finished the workout as well. I'll give you the next lecture. You can bring them.
Straight away. He's got comfortable pieces.
I just feel really bad because now I'm starting to get it's like everything was now it's like so like the side is like it's like
And you mentioned just to all your friends.
yeah, they were all really
They always get to that point when you hit, there's a turning point. It's just a bullshit. But I bet you got it nearly on.
yeah, I just worry bad because
But that's his own good way. Exactly. Have you ever thought about that? I don't want that. I don't leave it there. Too much. There's a chat. Yeah, I still think Freud would say he's still in that stage.
That's what I mean, ages. I think they just didn't relate to it.
We expect you to buy it. Shocking. You don't say this is why you are always paying brave it out for one day, brave it out and then go to bed at least. You actually well, just think about it, just think one day and then come to life and go back. No, I hadn't even my... You need to just tell me you're going to bed after this. The thing is, I have my okay, and the day One was I have a friend who's working here, and she wanted to pop up into my
yeah, I was gonna say
always think like George.
Next time, I will
Well,
just told them you're ready. There was some
but to be fair, I was perfecting, even though, to be honest, I was perfecting. There were some 25, we found each other.
Unless you guys go on research.
Bet they do care about the sound. You're a coward, you are. No. So, is it like having this? Yeah. You like why?
Because like, as long as you feel bad at you, then it's fine. Just can't be
But that's why I've done
Every time I talk to Galish, you can keep raising.
And these are the nice ones. Imagine if I
You are the nice one.
if they touch you, you break up with someone else. Also, that might only be whereas if I say like, no. Oh, I've met someone else, and then like,
Every time you just break my mind.
I told you at the start, you don't just think I should.
another sign I know
And not to mention, you're not trying to constantly say how much you're writing, you're not looking for positives, you're only looking for negatives. So once you're in that stage, because you are, even if you think it's something positive, you think, yeah, this is good, you always tell
Right, we're going to continue, please. Right, so we basically were saying about how we can represent the changes in properties while going through a heat exchanger using as well the 2D charts that you can find. And here, what I'm talking about is that you can see how a system is if you have a mixture and then you end up at this point in your vapor and liquid mixture. By going to this part of the chart, you will have the entropy of the liquid. And by moving through this part of the chart, you will have the entropy of the vapor. So you can have the entropy of each one of your components by looking at these slides. The critical points, obviously, will have the same entropy for both liquid and vapor. Right? And we can also know at which temperature and entropy, which is the phase that the system is at. Now, you normally will find a lot of these type of charts in books. And in here we basically have the process, how entropy changes with temperature. So when we have a liquid evaporation, then we will have an increase in entropy, while a vapor cooling or a condensation, a decrease in entropy, right? This is normally at the saturation point, so the temperature is constant during the saturation point. While heating a liquid, going up in the temperature, then we will have a slight, the slope is not that prominent. So we'll have a slight increase in entropy and slight decrease in entropy while cooling the liquid. And that's a typical temperature entropy diagram for a refrigerant 1 to 3. Okay, so you can have diagrams for a series of compounds and draw how things are happening. So now we have the enthalpy and the changes in enthalpy with respect to pressure. Okay, and that's again the pressure enthalpy chart for a refrigerant 1 to 3. And again we'll have the enthalpy curve, and we'll have the liquid on that side, the vapor on the other side. And here is when we have the enthalpy change of vaporization, which is the pressure will remain constant and the enthalpy will increase at that point. When we cool a liquid, then we will have a decrease in enthalpy on the liquid, and when we heat a vapor, an increase in enthalpy of that vapor. So they're not that difficult. Normally for heat exchangers, we will take them, this is just a repetition, as a constant pressure process, okay? The pressure changes there are pressure changes, but they can be considered insignificant. So, based on that, we can use these equations to refer to changes in enthalpy and entropy. And they're very similar equations that we saw where we're looking at first and second law and changes in entropy and enthalpy. So here we have the initial temperature of the liquid or the fluid, and then we'll go up to the boiling point if the liquid is going up to boiling point. If not, we'll stop at the temperature that we are basically we want to operate. CPdT plus the heat of vaporization plus the heat that is basically provided once the state of the fluid has changed to a vapor. The same thing happens with entropy, but the only thing that changes in the equation is that we divide versus the temperature. Temperature will be a function that as well needs to be considered. So this is the sensible heat of the liquid, the evaporation, and the sensible heating of vapor. So those are the equations that we are basically going to apply to design heat exchangers, which are the same equations or very similar equations to what we saw previously, but over there we were looking as well at changes in pressure. Since here we're just in a heat exchanger, pressure is not appearing. So let's have a look at this example. A flow of 1.5 kilograms per second of water passed through a heat exchanger where 165 kilowatts of heat are added. Calculate the temperature of the water at the exit of the heat exchanger. So here we are given the heat flow that goes in there, but we want to know what will be the temperature at the outlet. Okay, so imagine you are in a plant and you know how much heat is applied, but you don't know the temperature. So you want to know the temperature. So can you use these equations and solve for this, please? Here one thing, there is an error. 30 degrees Celsius will be how much? What should it be? 303. That's 303. So just change that please to 303 and solve it. The exam will consist of a series of problems as well, or examples as the ones we are doing. So I would recommend you always bring a calculator and be prepared to do some examples because we will keep on doing them during the lectures, and you learn more if you are doing it at this time. Okay. Right, so somebody has already solved it. So to solve this example, and this is not completely correct because that's taking into account the other one. But this is taking into account 308 instead of 303. So you can later on correct it, but the same principle applies. In here, basically, the first thing that we are going to assume, having this enthalpy, change in enthalpy, is that the liquid doesn't vaporize. Okay? So you always start like that. So if it doesn't vaporize, then actually the only thing that you're using is this part of the chart. And then Cp delta T, we also saw that basically is delta H, and delta H times the mass will be the heat that you need in the heat exchanger, right? We saw that at the beginning of the lecture. So we have the enthalpy inlet, but we don't have the enthalpy at the outlet. So we will use the heat flow in kilowatts that is given, plus the enthalpy equals to the enthalpy at the outlet. So the first thing will be to calculate the enthalpy at the outlet of the fluid. Then now, with the enthalpy at the outlet, then I can obtain delta H, right? So then, with delta H, we'll just use Cp T2 minus T1, which comes from the integration of dt. And we basically substitute the values. We take out T2, and then we obtain the temperature at the outlet. At that point, we verify if the temperature is less than 100 degrees Celsius. If it's less, that means that the calculation is right, and we can stop there. If it's not, if it's higher, if we obtain a higher value than 100, then that means that I need to start with taking into account the vaporization and the heating of the vapor. Okay, in this case, we can stop there, and then that's the solution that we get. Again, you need to correct that for the 303 that we have here. Right? So now let's have a look at the second example. So in this example, we have 0.4 kilograms per second of ethanol at 200 kilopascal are heated in a heat exchanger from 350 kelvins to produce a saturated vapor of 370 kelvins. A saturated vapor is a vapor at the boiling point of the substance. Okay, so we have ethanol. What is the boiling point of ethanol? Does anyone know? I think it's around 97 degrees Celsius. So it will be basically that, no? It will be the boiling point of the ethanol. When a saturated vapor is produced, is the boiling point of the ethanol, 370 calories. Calculate the amount of energy that must be transferred to the ethanol to produce basically ethanol to heat the ethanol and produce a vapor of ethanol at 370 and at this pressure. At 200 kilopascal, ethanol boils at 370, so that's one. Heat capacity of ethanol is this one, and heat of vaporization of ethanol is that one. So what will be the amount of energy transferred to the ethanol? So in this case, it's the opposite. We're given the inlet temperature, the outlet temperature, and we want to know the heat flow of the system. Okay? So in this case, we want to know Q. And Q equals M delta H. So we need to obtain that. So which equation are you going to use? Yes, so the complete equation that we saw at the beginning. So please just write down the equation and try to solve it.
here after getting the GMT data, use the Q is equal to GMT.
But you need to print this one.
Yeah.
Well, I did too far away, so I wasn't.
So it should 78 to then up to 78 to 97. So the person flash space over then I'm going to be higher temperature. So because we here if you know 78, this is 78, 1.1. So like this, this thing. Yes. Yes. No. You see, even it's saturated after you boil, after boiling, and you heat fat, it becomes saturated. So this is the final temperature. This one, T2. Then T boils. Here we should set 350 to 78. How do you go to 351? It will be 1.
Although to be fair,
Yeah.
I don't feel like I felt really bad.
From this one, this is 270.
Yeah, you're right, it's different. The only time I ever requested it was from because I didn't get my start and finish at sometimes at 6, 7. So I'm like, it's from one year, so like, you know,
What will be the
This one to this one, and then from 270 this one to the
No. Why are you actually zero? Very quick, try.
What is P1 temperature? P1.
so we are now
That's
guessing.
we are stuck.
Yes, it's not given.
maybe better, wasn't it?
Yeah, well,
Anybody got two boyfriends?
273.
You guess. That's the problem.
I'm going to call you the last one on your city.
Because at least if you get it, water right now, what temperature is it at? Is it at 0 degrees? Yeah?
No.
Yes. So why is
No,
it?
it's a liquid zero to some boiling point.
Why is it?
Benefit now.
I think it's from. So I think it's from 0. No, it can be.
No, not zero. 273 is zero.
Yeah, this is 0 because it's 0 degrees it's ice. So you for water.
That's why we don't see
Liquid from 0 to 1 gram.
No, at 0
I'm saying about water, I'm not saying about
yeah, 0 is ice.
No,
No, it's 0 when you at 0 it's quick. It depends on the atmospheric pressure, but we are doing the atmospheric pressure.
Does these things not trigger in his mind when you're saying at the moment?
Once you increase temperature to 1 instance, then you at 100 it boils. No, but you're guessing. If you get a liquid, any liquid, it can be at a certain temperature. Here, boiling is at 100. But you can take a liquid when it's at 25 degrees. So we don't know where they are starting from. But there they are going to produce
It's all natural.
heated in an exchanger from 350.
It's like that high city, like, obviously means right, so we both have to
That's it from.
someone
What does it mean? From 350.
here is a, you know, the word saturated. Saturated it's already boiling. It's already vapor. It's already vapor. So it means here.
No, yeah, the thing. From this, produce a separated vapor.
This one, which is boiling point temperature.
Yes, actually.
It's a boiling point.
That's why
Because you can see when I added 270, it's added 250.
It's a boiling point temperature. And then from this one to this one, you will have this one. T2.
From when?
From this one, this is boiling point temperature. Okay.
Yeah, but, so we don't need you.
Q1 is 270. For sure.
Why?
It should be like that.
No. 270 that's for water. No.
It'll be now live kind of there.
I stuck.
No, I have no
Yeah, waiting is this. Human, what have you used as your T1? What have you used as your T1?
Just stick to that.
Sorry?
What we disrespect.
Whenever I substitute anything, CP liquid and CP vaporization, we have two things, right? What will be the same?
Yeah, that's it.
It can't fizzle out.
CP for liquid. Yeah, we are here with the
No.
heat capacity.
I said it not. I said it not. I just guarantee.
This is CP for liquid. This is CP for liquid. It should
No,
be
you can tell the guys when they
Have they given?
get his best friend.
They have not given CP for
Big guy. It's so fucking awesome.
She has not
I
given
do
us
like
many
she was so
things.
oblivious to it.
We have made it for liquid. We have.
So, as a guy, you obviously know. But that doesn't take into account the fact that okay, so that makes it.
Yeah, that's liquid.
Sure.
Oh, absolutely.
It's not the nicest.
I think last T2 and T-boil are same.
Straight into something else.
T-boil might be
So when you
same.
were struck,
T2 and T-boil may be same.
You think so? So what have change nice pressure?
We'll have a
It will
little,
be zero.
the last integral might vanish, we have the first one.
they can't like it.
So you want an integral then?
Last year, I think.
So you can just open it like CP
So that's why.
and as this T constant.
Honest
No,
with
if
you,
it's not then the whole heat loss. So there is no change in the temperature, it's all integral.
Last method, I think, is
I'm thinking what I'm
So then,
I think T1 should be 350.
350.
350. T1 should be 350. On 350, you boil it to 370 degrees Celsius.
no, actually it's 350, it's already boiling.
but I, as much as careful people, he needs to
because maybe it will make it.
Because now, we don't
No, the question is about this boiling temperature. This is 350, it's already boiling.
So basically,
the
you
last
want,
equilibrium.
you want the
cough at the same time.
that will transform and then from liquid to vapor. That's the only thing that you want. You just want to evaporate the so
Oh, to vaporize.
you just want to evaporate anything that will cause if you evaporate the steam, water vapor. You just want to reduce water vapor. Not to go further. That's the only purpose. Because you need to supply vapor to your plant.
So that's integral.
Yes, so if you don't use more, it will get heat that is lost. Because your purpose was just to correct and the separation.
Yeah, makes sense.
Yeah, so here will be like 273 to 350.
This, if it's 350, 370, then you can put over. Then it will be no changes.
Yes, it will be the change, the temperature at which is starting, and the temperature at which you produce the vapor. Now, since if you were stopping here, then you wouldn't be vaporizing. We only have our liquid that is just about to vaporize. In order to make it vaporize, you need to pass through the heat of evaporation. So the heat of evaporation will pass you. You look at the chart that will look like that. The heat of evaporation will will basically make change from liquid to vapor. And that was the heat that we need to add in addition in order to make the fish change.
I know what so then what's the temperature?
The temperature doesn't change at the heat of evaporation.
So here it's constant.
No, you need first the change and after that you need to transform it. Right, so basically for this, it's just very simple. You just needed to do that. So you have the conditions. So you have to solve the integral for the temperature up to its boiling point. If we were having the chart here, let's say that we have enthalpy and we have temperature, okay? And then we have this. So basically the first thing is that we are increasing the temperature to arrive at the saturation line of the ethanol. And that's basically the first part, up to T-boil, when it says T-boil, right? If we were to stop in this first part of the equation, then we will still have a liquid. So we need now to apply more energy in order to do the change phase, or to change the phase from a liquid to a vapor, right? So this is the first part of the equation when we arrive here, and that's the second part of the equation. The equation that I'm referring to is the equation we just saw, which is this one, which is the same equation, very similar equation that we used when we were looking at enthalpy. Okay, so if you understand the first lecture, then you should be able to catch up this part. Now, we go from T1 to T-boil, so 350 to 370. We then add the heat to make the phase change. And that's it, we stop there. So this part will be essentially zero. Imagine that as an engineer, somebody is telling you, please, I just want to supply my plant with water vapor. I just want vapor into my plant. So the only energy that you will provide is to produce the vapor, and that's it. Energy additional that you produce, then you are heating the vapor, for which perhaps that plant is useless. So you are losing energy in there, right? So you just want to apply to the heat exchanger the energy needed to actually vaporize this ethanol and stop there. If you only apply the heat to arrive to the boiling point and don't apply more heat to make the phase change, then you still have a liquid at 370 kelvins, but still a liquid. So you need to apply more heat to make that liquid not change in temperature, but to make it change to a vapor. So basically, we are going through this chart at a constant temperature through the phase change or the saturation point. Do you get that? Is that clear?
What's the 700 then?
370? Where is 700? Where?
It's after the, yeah, no, above the, yeah. Right
That's the CP.
Excuse me, is that changing the enthalpy or
That's the CP.
that's now?
Ah, okay. Yes, the CP is different from this one. So it's 4 point. Oh no, is that? It's correct, yes. So that's CP. That's what I'm basically doing here is basically this will be Q for my equations, right? So Q equals M delta H. So I'm multiplying already by the M, so that's Q.
Oh, here is on the second brackets, I mean the last brackets, yes?
This one?
Yeah, 93 plus one.
Heat of vaporization is given.
Ah, okay, yeah. Wow.
So what is the first part of the equation? What is doing the first part of the equation? Heating to the boiling point. And the second part of the equation? Changing the phase from liquid to vapor. Right? Okay, so it's very important that you understand up to here, because right now what we're going to do is basically apply enthalpy and entropy from now on for all the equipment. So if you are struggling with this, then you have to go back and understand very well all these equations. Otherwise, you'll be lost throughout the course. So I will just start a little bit on compressors, but I won't be able to finish. So 5 minutes on compressors, and that's it. And it's just to look at these lovely pictures that we have here of the different types of compressors. So this is the second part, and this is basically, we want to change the pressure of the system. And normally we use a compressor in order to mobilize or to move a vapor from one way to another. And throughout the pipeline, the vapor will suffer energy losses. We want to keep the velocity going, so we have the vapor going through a compressor, or the gas goes through a compressor to apply energy to the fluid in order to move to the position that we want it to arrive. So in industry there are several different parts of compressors, but if you were in a plant and you will see a device, the basic change between a compressor and a pump is that a compressor always has a heat exchanger next to it. Normally pumps, they don't have heat exchangers next to it, and you will only see the pump in there. But if you see a device that has the compressor and heat exchanger, then, well, if you see something that has a turbine and a heat exchanger or an axial movement, that's a compressor, okay? And gas is going through that, so it's easy to locate in a plant where a compressor is. And that's because of these pressure changes affect a lot a gas, and therefore there is normally an increase in temperature. We will see that later on. But here we have this Excel foil compressor, where we basically have the liquid going through here, and then this starts moving, more or less like a centrifugation system. And then through that movement, we're basically applying kinetic energy to the system, and therefore increasing the pressure. The movement of the molecules start to move faster, and therefore, since the size of the vessel doesn't change, there is an increase in pressure. So here we can see a compressor, and this will be basically the Excel part of it that will be moving. So they're normally very big equipment in a plant. We also have another type of compressor, which is the reciprocating compressor. And in here, what basically changes is the movement that you have inside the compressor and how you are applying this kinetic energy into the system. And the centrifugal pump, which is the same way that it works for a liquid or a gas. So the application of what type of compressor you will use depends which pressures you want to achieve in the fluid. So for instance, if you want to increase the pressure significantly, and as well as which temperatures you can allow the fluid to go through. So normally, gas and vapors will consist of this type of equipment, compressor expander, and liquids will normally, you'll change the pressure of liquids through a pump. So in a compressor, we go from low pressure to high pressure by applying work. In an expander, we go from high pressure to low pressure and then producing work from there. In a pump, we apply work, and then we go from low pressure to high pressure. What would be the opposite of a pump in that case? If you want to go from high pressure to low pressure.
High pressure to low
On a
pressure.
liquid.
Expander, you say?
Expander is normally for a gas.
Ah, for the liquid, you use like higher
Like you, sir?
diameter.
Normally it's called a turbine, right? So you can do both movements in the one or the other. But here we're going to look at gases and vapors, basically, because pumps are quite easy to design. You don't need a lot of energy balance. You do an energy balance, but basically apply kinetic energy, potential, and pressure energy. So in compressors and expanders and pumps, no heat is transferred to or from the fluid, only work. So the enthalpy balance becomes M delta H will be equals to the work applied. Now this is another assumption. Here we only apply work into the system. These processes are irreversible, and we have to take that into account in doing calculations. So for irreversible processes, then we will have to take into account changes in entropy, unless we assume that it's a reversible process, which is something nicely done for compressors, and we solve a lot of our problems. Okay? So we will stop here, and on the next lecture we will look at these compressors part.
I can't ask anymore, that's fine. The last thing you need right now is my second job. You say that's because there's no room for it. So Dan's got always.
Yes, I think that there are some examples in Smith, but well,
I forgot all of them.
in Smith, I think Smith would be the one that I use the most.
Shall we do it in Spanish or in English?
Huh?
Shall we do it in Spanish or in English?
No, tell me in English.
Why, in the first example, we add the vapor enthalpy, and why not we just do sensible heat of the liquid plus latent heat plus sensible heat of the vapor? We also add the enthalpy of the vapor. to calculate the change of enthalpy in the first example.
That will be the latent heat.
No, we have 4 terms.
In the first part,
Yeah.
for the temperature, because we assume that the liquid is not vaporized. We assume that the liquid, that's the first assumption. We first assume that the liquid is just heated before arriving to the saturation point. The problem will be if we then get a temperature that is higher than the vaporization,
But
or that
there
arrives.
is a phase change in that example, right?
No,
No,
it
no,
was
there is.
water, and we arrive at
But
73.
sorry. Not the example from today, the example from last class.
Ah,
For the first
which
law.
one? Here? So which example?
Yeah, the example of the diagram in this one.
Uh-huh.
So we have this from here to here, that would be sensible heat of the liquid.
Uh-huh.
From here to here, latent heat.
Uh-huh.
And from here to here, that would be sensible heat of the.
Uh-huh.
But then we add the enthalpy of the vapor.
That will be this part, no?
No, we have four terms. Easy.
Where? That's the entropy. So you want for the enthalpy, or
Enthalpy, yeah, enthalpy.
enthalpy, okay? So enthalpy, sensible heating of the liquid, evaporation, sensible heating
But
of
at
the
the end,
vapor. I don't know, that's like...
there's another
No,
one.
the final one was the compression.
Yeah.
We just add them
I think-
together and then do the
I think it's
compression.
still missing because I was revising them yesterday. And aside from this one, there is another one because here there is not the.
So
let's
the
leave it
next
for-
one was the pressure. Check it and we can look at it next time if you want. Okay? See you.